We end tonight with the clearest images yet of Neptune, the most distant planet in our solar system, a world shrouded in swirling methane-rich clouds and violent winds that have long kept its secrets hidden from Earth. For decades, astronomers could only glimpse fleeting glimpses of its icy surface and dynamic atmosphere, leaving much of its behavior a mystery. But everything changed when the James Webb Space Telescope, humanity's most powerful eye in the cosmos, captured something extraordinary, an event so massive and sudden that it could rewrite everything we thought we knew about the outer solar system. A collision unlike any seen before, shaking Neptune's distant realm and sending ripples of energy across its atmosphere, offering a window into forces at play in the farthest reaches of our planetary neighborhood. At first, the James Webb Space Telescope hadn't been looking for disaster. It was simply observing Neptune as part of routine monitoring of its cloud formations, atmospheric shifts, and magnetic field behavior. Then, during a scheduled deep space observation, astronomers noticed an unexpected spike in infrared radiation, a burst that didn't fit with Neptune's normally cold and uniform thermal signature. Alongside this, the planet's outer cloud layers showed a sudden dramatic disturbance, too significant to be dismissed as ordinary weather. Analysis of the infrared data revealed that the energy had come from an external source, traveling at high velocity, ruling out storms or internal convection. Modeling and spectral analysis suggested that the object responsible measured between 30 and 50 kilometers across, roughly the size of a large asteroid or small trans-Neptunian object. Because Neptune's thick atmosphere prevents direct imaging of a surface scar, scientists instead tracked the impact through shock waves, radiating across the southern hemisphere, temporarily distorting its faint rings and creating a bright thermal hotspot that had never been observed in decades of monitoring. The event was accompanied by a lingering trail of debris, likely from the colliding body suspended in the upper atmosphere, a hazy arc visible in both infrared and visible wavelengths. The impactor's composition, mainly volatile ices and rock, suggested it might have originated from the Kuiper belt, nudged off course by gravitational forces, perhaps even from Neptune itself. Beyond the immediate visual and thermal effect, the planet's magnetic field and local charged particle environment were disturbed, hinting that the collision had consequences beyond the atmosphere, potentially affecting internal convective layers responsible for generating Neptune's complex and tilted magnetic field. This sudden high-energy event revealed that even in the distant, seemingly stable corners of our solar system, violent and transformative processes are still very much alive. The collision on Neptune has prompted scientists to reconsider long-standing assumptions about the outer solar system's stability. For decades, astronomers believed that such massive impacts were largely relics of the solar system's formative years, when debris was abundant and planetary orbits unsettled. Yet this recent event demonstrates that even today, rogue objects from the Kuiper belt or beyond can wander into Neptune's path, capable of unleashing colossal energy upon impact. The implications stretch far beyond Neptune itself. By observing the shock waves, atmospheric disturbances, and ring perturbations, scientists can study impact mechanics on a scale that Earth-based observations cannot replicate. This offers unique insights into energy transfer, atmospheric chemistry changes, and the behavior of magnetic fields under sudden external stress. Moreover, it raises urgent questions about planetary defense. While Earth is protected by continuous monitoring and early warning systems, Neptune's collision underscores that large, high-velocity objects can still traverse space undetected, highlighting the importance of tracking smaller, distant bodies that might eventually threaten inner planets. The debris and thermal footprint left behind serve as a natural laboratory, allowing researchers to study how planetary atmospheres absorb and dissipate massive amounts of energy, information that could be crucial in understanding not only our solar system, but also the dynamics of exoplanetary systems, where similar collisions could shape atmospheric composition and magnetic field behavior. In essence, the Neptune collision is a vivid reminder the outer solar system is not frozen and passive. It remains a dynamic and occasionally violent region, reshaping our understanding of planetary evolution and the continuing activity of celestial bodies, even billions of years after the formation of the Sun. The aftermath of Neptune's collision revealed unexpected and intricate details about the planet's atmospheric and magnetic behavior. As shock waves propagated through the dense layers of hydrogen, helium, and methane, instruments aboard the James Webb Space Telescope detected dramatic changes in cloud velocities and turbulence patterns, indicating that the planet's powerful jet streams had been temporarily disrupted. The disturbance didn't stop at the atmosphere. Neptune's already unusual magnetic field, tilted and offset compared to its rotational axis, showed signs of short-term anomalies, suggesting that the impact had reached deeply enough to influence its internal convective motions. Simultaneously, the faint arcs of Neptune's ring system flickered with increased brightness as particles and debris from the collision interacted with the rings, temporarily altering their structure. Spectral analysis further revealed chemical changes in the upper atmosphere, with elevated concentrations of hydrocarbons and nitrogen compounds, either deposited by the impactor or produced by shock-induced reactions. These chemical signatures provide vital clues about the composition of both Neptune and the impacting body, offering researchers a rare glimpse into processes that could mirror conditions on distant exoplanets. The combination of physical, magnetic, and chemical disturbances illustrates that Neptune's response to such a collision is multifaceted, revealing the planet as a living, dynamic world rather than a distant, static ice giant. Each observation, from the shifting clouds to the magnetic ripples, adds a piece to the puzzle, allowing scientists to model not only Neptune's internal and atmospheric mechanics, but also the broader dynamics of ice giants in general. This event has effectively transformed Neptune into a natural laboratory, one where extreme, large-scale impacts can be studied in real time, providing insights that extend far beyond our solar system and into the study of planetary systems across the galaxy. The discovery of Neptune's collision has far-reaching implications beyond the immediate physical and chemical effects on the planet itself. For decades, scientists have assumed that massive impacts were largely confined to the early solar system, billions of years ago, when debris fields were dense and planetary orbits less stable. Yet this recent event demonstrates that even in the current era, the outer planets remain vulnerable to high-energy collisions from rogue objects, particularly Kuiper belt objects or stray trans-Neptunian bodies. The sheer size and velocity of the impactor suggests that these distant regions are more dynamic than previously thought, with gravitational interactions subtly shifting objects into potentially catastrophic paths. This realization compels a re-evaluation of celestial risk, even for planets far from the Sun, and provides a stark reminder that cosmic events can occur without warning. Moreover, observing such a large-scale collision in real time gives scientists a unique opportunity to study impact mechanics at a scale impossible to replicate on Earth. From the propagation of shock waves through dense atmospheres to the chemical transformations triggered by sudden energy input, Neptune acts as a natural laboratory for planetary scientists. The event also underscores the importance of continuous observation, as traditional ground-based telescopes might have missed the infrared spike entirely due to atmospheric distortion or insufficient sensitivity. In addition, the collision offers insights into planetary defense strategies, highlighting the need to understand the distribution and movement of large, distant celestial bodies that could one day threaten Earth. Beyond practical concerns, this occurrence reshapes our understanding of planetary evolution, showing that outer solar system bodies continue to experience dramatic transformations, driven by forces still largely hidden from our observation. Neptune, once viewed as a quiet, distant giant, now exemplifies a system in motion, responding dynamically to collisions that have echoes not just locally, but potentially across the broader architecture of the solar system. The aftermath of Neptune's collision revealed a cascade of intriguing atmospheric and magnetic phenomena that continue to captivate astronomers. Following the impact, the planet's upper layers exhibited pronounced turbulence, with high-altitude clouds shifting rapidly and jet streams momentarily accelerated or redirected. These changes created temporary distortions in the planet's faint ring system, suggesting that even the most delicate structures were influenced by the shockwave's propagation. Spectroscopic analysis uncovered an unexpected rise in hydrocarbons and nitrogen-based compounds, either remnants of the impactor or products of deep atmospheric chemistry triggered by the intense energy release. Such chemical shifts provide a rare glimpse into the inner workings of an ice giant's atmosphere under extreme conditions, offering a proxy for understanding exoplanetary atmospheres subjected to similar high-energy events. Beyond atmospheric science, the collision sparked renewed interest in comparative planetary studies, especially regarding Uranus, a similar ice giant yet far less explored. By analyzing Neptune's response, scientists can refine models of planetary formation, stability, and internal dynamics, gaining insight into how violent events can alter magnetic field generation, atmospheric circulation, and even long-term planetary evolution. The incident also raises critical questions about the prevalence of rogue objects and Kuiper belt bodies, challenging assumptions that the outer solar system is largely static. In short, Neptune's dramatic encounter is more than an isolated spectacle. It's a window into ongoing processes that shape not only our planetary neighbors, but the broader architecture and dynamism of the solar system. The Neptune collision has far-reaching implications for planetary defense and observational strategies, emphasizing both the limits and the potential of current space monitoring capabilities. While the James Webb Space Telescope fortuitously captured the event, it was not designed primarily for solar system surveillance, highlighting the chance nature of its detection and the need for dedicated monitoring of distant planetary bodies. Ground-based telescopes, even those equipped with adaptive optics, might have missed the rapid infrared flash entirely due to atmospheric distortion and Neptune's faintness, revealing gaps in our ability to observe sudden high-energy events in the outer solar system. This realization has prompted astronomers and space agencies to consider enhanced tracking systems for Kuiper belt objects and other rogue bodies that could pose risks not only to distant planets, but, in extreme cases, to Earth itself. Additionally, the collision provides a natural laboratory for studying planetary-scale shockwave mechanics, energy transfer, and chemical alterations in atmospheres composed of hydrogen, helium, and methane, data that can refine our understanding of exoplanets and their responses to impacts. The disturbance also offers insight into Neptune's magnetic field variability, suggesting that even a single high-velocity collision can temporarily influence charged particle environments and convective motions deep within the planet. In essence, this event serves as both a cautionary tale and a treasure trove of scientific data, compelling humanity to rethink how we monitor, understand, and prepare for the dynamic forces still active in the far reaches of our solar system. The chemical aftermath of Neptune's collision continues to captivate scientists, revealing changes in the planet's upper atmosphere that may provide clues about both the impactor and Neptune itself. Spectral analysis detected elevated levels of hydrocarbons and nitrogen compounds, far above normal concentrations, suggesting either debris from the impactor or deep atmospheric reactions triggered by the shock and heat. These chemical shifts offer a rare opportunity to study how extreme energy events alter ice giant atmospheres, with direct implications for understanding exoplanets in similar conditions. Beyond chemistry, the impact has intensified interest in comparative planetary science, as researchers now have a real-time case to study how gas and ice giants respond to massive collisions. Observing Neptune's atmospheric waves, jet stream disruptions, and transient ring disturbances allows scientists to model similar events on Uranus or other distant worlds, improving predictions of planetary evolution and stability across the outer solar system. This unprecedented collision challenges long-held assumptions that the distant planets are static, frozen realms, revealing instead a dynamic environment, still vulnerable to high-energy cosmic events. It also underscores the need for continued monitoring of Kuiper Belt objects and other potential threats lurking beyond Neptune, as even a rogue body from the outer reaches can produce planetary-scale consequences. The broader scientific community is now mobilizing, with Hubble, ground-based observatories, and international facilities adjusting their schedules to track ongoing changes, study debris dispersal, and measure long-term atmospheric effects. Each new observation promises to expand our understanding of outer solar system dynamics, showing that Neptune is not merely a distant cold giant, but a stage for ongoing celestial drama, offering insights that could reshape planetary science for decades to come. The implications of Neptune's collision extend far beyond immediate scientific curiosity, challenging our understanding of planetary defense, outer solar system dynamics, and the prevalence of large celestial bodies lurking in the Kuiper Belt. While Earth has long been the focus of impact monitoring, this event is a stark reminder that even the most distant planets remain vulnerable to high-energy collisions, suggesting that similar rogue objects could pose unseen threats closer to home. The data from JWST, combined with follow-up observations from Hubble and ground-based telescopes, provides an unprecedented natural laboratory to study shockwave propagation, atmospheric chemistry, and magnetic disturbances on a scale impossible to replicate on Earth. Moreover, the collision offers crucial analogues for exoplanetary studies, helping astronomers interpret atmospheric anomalies on distant ice giants orbiting other stars. Beyond pure science, this event sparks profound philosophical and strategic questions. How much do we really know about the stability of our solar system, and could similar collisions occur without warning? It also emphasizes the value of persistent, high-sensitivity observation infrastructure, as JWST's serendipitous detection highlights the potential for groundbreaking discoveries even outside an instrument's primary mission. For planetary scientists, astronomers, and astrophysicists, Neptune's recent collision is more than a rare event. It is a call to rethink the outer solar system as a dynamic, evolving environment full of surprises and hazards, where massive cosmic events continue to shape planetary atmospheres, magnetic fields, and even ring structures in ways previously thought impossible. As we continue to study the aftermath, each new piece of data sharpens our understanding of celestial mechanics, planetary resilience, and the ongoing interplay between the solar system and the countless bodies that traverse its outer reaches, proving that even in the farthest corners of our sun's domain, cosmic drama is far from over.